So in my last video, I described a pretty rough outline of how my world generation works in Godot, and after a lot of improvements and optimizations, I think a deeper dive is finally ready. Since chunks are the foundation of the world, I'm going to start there. How are chunks generated? Since the world is divided into a 2D grid of chunks, it's a lot easier to gather them around the player. When the player is spawned in or moves to a different chunk, I gather the new chunks in a growing spiral. This means the nearest chunks are prioritized for updates since they're the first element sorted. Once all the chunks are gathered, I sort them into 3 categories: to be generated, to be killed, and to be updated. When a new chunk is requesting to be generated, I always assume its LOD is the lowest it can be. Since new chunks are always going to be at the furthest point from the player, this means I will generate that chunk at the lowest resolution. When generating those chunks, I use the resolution to determine how the mesh is built. To ensure chunks are always the same size, I use the base chunk size and divide it by the resolution to get the vertex spacing. This spacing multiplier is to assert the chunk size no matter the resolution. Now, we can loop over the size of the chunk and build the mesh. For each point, I sample the height using a combination of functions. These functions come from a built-in resource depending on the chunk's biome. Each biome resource samples a unique height map with a different math function to return varying results. This allows me to make terraces, canyons, mountains, and other shapes. These generators, as I call them, are stored in the biome node for quick access. What they store is dependent on the biome, but in general, they store a height map, a map for spawning decorations, and 2 curves, one for erosion and one for detail. These curves act as a strength multiplier for the global erosion and detail maps. For example, in the desert biome, the erosion and detail curves look like this. When a point from the global maps is selected, they are compared to the curve to find the strength that point has on the overall terrain shape. By sampling points on each vertex of the mesh in the desert biome, you can see how the curves shape the terrain. Erosion is the large-scale parameter that creates divots, holes, and other carved shapes. Detail is the fine terrain pass. It refines the shapes and adds small-scale variations. After sampling the height, I can construct a mesh from the newly gathered vertex positions. All the mesh data is done on a separate thread, which is tracked by the main thread. To ensure the thread is finished and the data is safe, I don't allow any write calls to variables outside the thread scope. The read calls are also limited to read-only data to ensure the data is not corrupted. When this thread is finally finished gathering the data, I use a function to release the thread and spawn in the new chunk. Some of you may be aware already, but thread generation is an expensive task that requires a lot of overhead. World generation, as of right now, is capped at 4 active threads at once. These threads are a call it and forget it system. I only care about the return result. So to help visualize, the game gathers new chunks. These chunks are then sent to a loading queue where, on a per frame basis, they are loaded and their thread task is sent out. Now, the main thread awaits the result. When this result is returned, the main thread constructs the mesh and sends it to the chunk for updating, and that thread is freed, allowing for another chunk to be loaded. This is done for each new chunk gathered. Once all those chunks are finished, they are added to a dictionary for tracking and updating. Since we have this dictionary of what I call safe chunks, these are chunks that are no longer in use by a thread and have finished loading, we can use this to delete chunks that are no longer in view distance. Deleting chunks is really simple. They're sorted from the gathered spiral chunks using view distance. To prevent lag when deleting chunks when using a large view distance, I send these to be deleted chunks to a queue. This queue is pulled from once per frame instead of mass deleting them all at once. Afterward, I clean up the dictionaries and other resources that reference that chunk's key. Now, we can move on to updating chunks that are already loaded. To optimize rendering, chunks use an LOD system for reducing the vertex count the further away a chunk is. As the player moves closer to these chunks, their distance is computed to find the LOD index to update to. If that chunk has already generated this LOD level, I just reuse the mesh. If not, I use the same chunk generation code to create the new mesh at the LOD level and swap it in afterwards. Now that a chunk can be generated, deleted, and updated, how is the chunk LOD chosen? When fetching a new LOD, the chunk's squared distance is compared to the player. Then, I return the index in the loop at which the comparison happened, only if it is less than the LOD distance. All of this, the generation, updates, deleting, etc., occur in loop queues to alleviate the per frame workload. But how do chunks know their biome? When a chunk is spawned, its position is used with a biome generator to fetch the biome type. On startup, a hash map is generated of biome origin points based on noise parameters. This map contains biome points where the key, a 2D vector position, is stored alongside the biome name. These points are chosen based on the moisture and temperature noise maps. When a chunk is requesting its biome information, this chunk's position is used, or its chunk key, along with a search radius to find the nearby biome points. The distance to these points is the strength of the biome. This strength parameter is used to blend biomes with each other using linear interpolation. It is also used to tint the chunk's color. Although each biome is used for the chunk's generation, only the strongest one is chosen as its core biome. This biome takes priority for animal spawning, forageables, decorations, and other things. So now, the chunk has its mesh, LODs, and its biome. All of these are combined in an ordered system to create chunks. Next in the system, decorations. During the still ongoing process of generating the decorations, I've gone through several iterations. To start, the first 3 to 4 iterations of the system, I used multi-meshes to spawn and hold the decorations. These multi-meshes are great for thousands of objects, but since each chunk creates new, unique multi-meshes, I had problems with draw calls. Assuming you could see all chunks at once in a 32 by 32 radius, rendering one type of multi-mesh would take at least 1024 draw calls. The multi-meshes are not batched together, so I continued using this system since the speed of creating buffers for multi-meshes outweighed the cost of draw calls until I started adding more decorations. So pretty quickly it became unplayable. Looking into the distance or through a dense forest would drop the FPS by around 40 to 50 frames. It wasn't due to the number of triangles, but the sheer volume of draw requests being sent. To solve this draw call issue, I switched to using individual mesh nodes for each decoration. Now, instead of 1024 draw calls for 16,000 trees, it's 2. This comes at the cost of speed and memory, but both of these problems are things that can be solved or at the very least alleviated. Draw calls are a different breed of problem. They require changing the fundamental way the meshes or textures are drawn and instantiated. Managing speed and memory is, at least in my case, easier. Anyway, since each biome has its own clutter or decoration map, I use those to sample random points in the chunk size. When a point is selected, it is compared to the decoration's noise threshold. Each decoration has its own strength at which you would like to spawn. This lets me control the density of specific decorations and the manner in which they spawn. By using cellular noise for decorations, I can assume the threshold for a decoration is a ring. This means I can spawn mushrooms in and around forests, dead trees around living ones, and even small saplings around adult trees. After that pass is true, I compare it to the normal threshold of the decoration. The normal is essentially the maximum angle at which the decoration is allowed to spawn. This prevents trees from spawning on, let's say, a 75-degree cliff or whatnot. Once those arguments are passed, I can finally spawn the decoration. These decorations are actually processed during the mesh generation for that chunk. Since I'm already using a thread for the mesh, I just use the same thread to compute the transforms for the decorations as well. The decoration result is passed alongside the result of the mesh data. Once all is finished, the main thread offloads the decoration task to its specific handler, sending key information with it. Once the information has arrived, it immediately goes into another queue. You'll notice that every task on the main cycle is queued for less per frame workload. When it is time to load the decoration from the queue, it goes through 3 stages: initialization, resource loading and caching, then spawning. Firstly, a dictionary is created to store the meshes and their transforms. Why not an array? Code clarity. I don't like using arbitrary numbers where I can assume I know the information being passed and accessed. Then, I unpack the array of floats that was created by the thread that store the individual decorations' positions and turn them into transforms. Alongside that, I'm grabbing from a pool of mesh instances. After the transform is packed, I assign it to the mesh instance and store the dictionary containing all the information. I now assign these meshes to a list to keep track of all active decorations. While this list is storing loaded decorations, there is also a separate operation going on. In the background, I am loading and reusing the meshes for the decorations. I don't want to load new resources every time, so I cache them. But I can't freeze the game to wait for a decoration mesh to load, so what do? On a frame-by-frame basis, I have a resource loader class track this. When a new decoration is requested, its mesh instances are being created while the actual array mesh for the object is being loaded. When the loading is complete, the list is accessed and the mesh instances are assigned the loaded mesh. Then, the mesh is cached using the resource's string path. All of this combines to create the decorations on each chunk every time a chunk is loaded. These processes all working together complete the world generation system.